my name is Xinge YU. I'm from City University of Hong Kong. First, I would like to thank Professor Tao and Professor Yan and Professor Zheng for the invitation. So I'm very honored to attend this great event to share our recent work. So the skin electronics, especially for the intelligent sensing. Another area is the actuation. We call it the touch VR. So first, I would like to take a couple minutes to briefly talk about the motivation and a very hot topic recently. So we know it's a metaverse, right? So which was suggested by Facebook, now named Meta. So especially in the past 1 or 2 years, so the world changed a lot, especially due to the pandemic. And so the economy and also the people's lifestyle changing from the offline to the online. And then, so it's accelerates the virtual progress, the interaction with the computer devices. So taking one example, like one scenario, for example, that's the online meeting. So now everybody is taking online meeting. Even so now it's very exciting to have this hybrid way. There are still like over hundreds people online. So the Meta gave this solution is that in the online meeting, if we can have a 3D glass and we can interact with each other people, like shown here, you can see that. So in this case, so the people who attend the online meeting can see your face, your emotion. However, so it still seems a long way to go. So that's quite beyond. So the quite big so picture that's suggested by Facebook. Next, I'm going to give you like a short video to show the idea of metaverse. I think this video gives a very clear idea. The name is Ready Player One. So in this movie, so it's described in the near future world. So everyone plays video game. They use advanced instrument to control a gaming character. So in the game. And the character is closely interact with the user in the physical world. Pay attention to this scenario. One user is interact with the other one, and he can actually feel the touch from the other one. And so we call this the virtual touching, or you can call it the touch VR, okay? And I think this is the final version that's the metaverse want to be. So however, we know, so it's still have a long way to go because we did a lot of efforts on pursuing visual stimulation, auditory stimulation, and we also awarded a lot. So we know the pursuing of visual stimulation allow us, the engineers, so to develop the high resolution display, so in the movie and all this type of devices. Will the pursuing auditory stimulation so allow us to have the like earphones and so speakers? My question is how about a tactile? So which is the one of the most important sensations, so among the 5 sensations. So there are some haptic interfaces or technologies nowadays, but you can see that. So like the cell phones, very simple vibration. All these are handheld, so very bulky, so down mode, low resolution, vibrated based, so haptic interface. So we want more. So more things is that equally important, always compatible to these visual or auditory stimulation. So let's still use the movie, for example. You see, the real situation is the user feels someone is touching him. So, and the virtual situation is like this. So you can never so achieve this scenario use the current so haptic interfaces as I shown here, right? So because you use handhold it. So in my opinion, if we want to realize such interface, we need to meet the requirement. The first one is a thin, soft, wearable, since you can see that device on the body, right? And another thing is you don't want to only feel the simple force. You may also want to feel the temperature and the texture, all these complicated information that provides on your body, which is quite so related, similar to the real touch. So we give some solution, and so this is our first generation. So I think so. Professor John Rogers also mentioned a little bit of this work. So in yesterday's so talk, and so This work was started in 2017. So when I was still a postdoc fellow in John Rogers' group. So we initiated this idea, how about we create some wearable devices that can provide habitat feedback, force feedback, rather than we only like sensing some physiological signal, temperature like that. So we do the reverse way. We provide electricity and then we generate the force, but this force on our body, we call it feedback. And this is the first generation of the technology. You can see that. Think about it, if we just peel a piece of clothes from the Ready Player One, so that boy. And you can think about it. There's multiple points of the habitat actuators on it. So in such a small area, we can integrate 32 mechanical actuators, and each one is driven by electromagnetic field. So when you input AC current or voltage into the cup coil, so alternative magnetic field will allow the magnet to vibrate, and then you can feel the feedback. And of course, we use a lot of electronics integrated in the system, and also use this skin color tone encapsulation layer for ethnic purposes. And there are a lot of devices, and these are stretchable design, so in the device. So even the device contains hundreds of these small components. Will we use the microfabrication technology and the integration strategies can make all these devices so in a very thin and a soft format, which is only in millimeter scale. And in this case, you can just mount the device on different part of your body. So one thing I will mention is, so we know the people have the different curvatures, so the bone and the skin, and we can just along these curvatures to make the device so the different customized shape, and so which is very comfortable to wear, and also exhibit a very good mechanical performance. So one thing, so it's very important for the mechanical actuators. We need to know more about our skin. So the most important things, if we want to use some very simple actuator and providing force feedback to our skin, so it seems very reasonable to find our most sensitive frequency that the actuator can provide. So from this table, you can see that around 200 Hertz is our most sensitive frequency. And you can also have the experience from daily life. So from the cell phone vibration, that is exactly 200 Hertz or around that. So the thing seems very simple. We just make the actuator working at 200 Hertz. And we want it resonant at 200 Hertz. That means if you input 200 Hertz so signal, the device will be working very intensively. So we call it the resonation. And then you save a lot of power and also get a very high force output. So you just simply tune this cantilever-based mechanical actuator or the handling. And so you can tune the frequency from 100 Hertz to 300 Hertz in this range. It's tunable. Another thing I want to mention is when you just randomly arrange different actuators in an array, one thing may happen is we call mechanical coupling. When this actuator is working and you feel this whole area have some force feedback. So it's very simple. You just arrange the angle of the two actuators like a 45 degree, 90 degree, and a 270 degree. The mechanical coupling can be decreased less than 6%, and you don't feel this coupling anymore. Okay, so this is very specific circuit design, which include two parts. We have the wireless powering part, and the other is the wireless control part. So if you want to know more, we can discuss later. And so let's keep going on. This is a show how our device is working. So this is a self-made GUI interface, and this is the device. When you put the points on the touch screen, and each point can provide the feedback on the device, and you can feel use another hand. So that is corresponding in real time. Okay. But however, so since I mentioned it's vibration, it's very hard to see so how the device is working. So we conduct a visible experiment. So to make the vibration is visible, we use the laser as the reflector and project on a wall. And when the actuator is vibrating, the laser, so optical will liberate the vibration to a very large fluctuation, and you can clearly see it. So this is another software we developed. So here you can see we can not only let one single point to working and associate with the point you touch on the screen. And you can also write an array such as a letter. Here we first write a letter N, and you can see that. So we press start, and all these N patterns will be working, and then it's a U, and it will also write other letters like a CTU. You can see it's very clear. You can distinguish the different working areas. So when it's vibrating, okay. So based on the system, it's very simple for us to think about the potential applications, such as gaming. That's everybody can think about this one. So just use like a fighting game, for example. So if the gamer wear these devices on different parts of the body, and he is control this gaming character. So whenever he's punched or is punching other people, the contact area of the body in the game character will provide force feedback to the real situation, and you can feel that for the immersive gaming experience. Another area is social media. And think about it, so in the pandemic area, if we can touch our family members in a long distance, which can become true based on our device. And here, so we give another like demonstration. Well, this case is where these haptic devices, and so do the video chat with a family member. And when the family member touch, so the boy on the screen, and he can actually feel this touch. So we call this, so there's a long-term touch. So another area is pretty sure for the biomedical engineering application. That's a prosthetic sensing and control. So we know there are a lot of disabled people, including the amputee person. So even though they can have a very nice prosthesis, so the robotic arm. So however, so basically you can control that, but you cannot feel that when you use a robotic hand to hold something. Well, if we put our haptic interface on the end of the empty arm, and the sensor and the Internet of Thing can send the information back to this haptic interface, and he can not only touch, he can also feel. So it can provide comprehensive touching information, such as force. And based on this device, the user can actually can control the force and to hold like an object more precisely. However, there are still a lot of challenges to reel such a thing into a system level product or devices. So even like now the biggest, one of the biggest companies, so Meta, Facebook, so even they released the glove to provide some haptic feedbacks. You can find that there are a lot of challenges in it. So such as using the pneumatic air bubble is the pumping and depumping. Of course, there will be time delay. Another thing is, to me, I don't think the resolution is high enough. And second thing is, and most important thing, it need to connect with a specific instrument and to pump air and depump. And the user need to have all of these, he can realize such tactile feeling. So which is impossible for the most of the users to use it at home. So we give the solution. So we know there's another idea called the electrotactile. You provide electricity to your hand and then all your body, and by changing the input signal, so from the intensity and frequency, you can get a different tactile feeling by stimulating different depths of your skin with the different mechanoreceptors. And here, so we make such system very thin, soft, which can be mounted on the hand. And so the control panel is also very thin. Then So the user can like use the VR and feel the haptic feedbacks in the VR application scenarios. And here we use the connector either with the cell phone or the laptop. And another purpose is we know different people may have different thresholds. So some people may don't feel hurt even so you use very hard punch on his hand. A lot and some like especially small kids, even very tiny fault he may or she may feel hurt. So a customized threshold identify function for this device is very important. So this device has such function. So by different users, you can just tune it. So and realize the and find the threshold. You can see that we can optimize the input, and so we call this the decoding of the tactile information by our haptic device. And so by different people or different genders, we can all make it happen. So with such system, we can do a lot of application. First one is connect the VR glass and to provide a simple touch feeling. And you can see here, so the device is completely wireless control and connect with the computer. So unfortunately, so the VR glass is not, okay, it's not our fault. You can see that, so the student is holding and touching this one. And so it really feels the touching feeling. Another thing, an advantage of such system is the electrotactile can provide a very strong intensity. You can even feel hurt. So such as here. So when the students try to touch a saguaro, you can see because there are thorns on it and it's spurted and it can feel very hurt. And so it's trying to touch it, and when you really touch it, it's just feel very hurt and can put the hand away immediately. So it's not only can be integrated with VR, but also AR. You can just use the camera to capture and to connect with the current video game. And you can see that. So the small mass is running on your hand, and whenever you walked anywhere, you can feel these tactile feelings. And not just like this. So you can also collect all these tactile information when the mass is running on it. You know, so now the information means everything because big data. So they need information, they need data. So another thing is not only interact with the virtual, but the real thing. We can also use our haptic interface to interact with a robotic hand by integrating some sensors in it. When the robotic hand is holding something, you can just feel that. In this case, so you share the similar, or even the same tactile feeling with the robotic hand. So later on, I will tell you why this is very important. So I mean, so this you can actually think is a human-machine interface, even for the prosthesis control and sensing. So robotics is the robotic arm, and so the machine, this is the machine, and so the human is the user. And so our device can be the interface, okay? So think about it, if you can control robots, and the robots can do whatever you do, like just a one-to-one copy your motion. And so the sensors on the robot can send all these tactile information back to your body. All the things is wireless, so no very bulky instrument. So wireless control and just mount it on your skin. So it will be very important. So we call this a robotic VR, okay? So we for the first time suggest this idea using the skin integrated electronics. So we not only include wearable sensors in the system, we also include these haptic feedback devices in the system. So for this purpose, so we can control a robot, and so the robot can do the similar thing. And this is how we design the system. And so in the system, we have 7 sensors and 5 actuators in one small patch, which is all wireless. And you can mount as many as these patches on the user's body to control different many degrees for more comprehensive manipulation of the robots. And so the sensor, so we we use and we fabricate developed is very thin soft. You can see it's almost conformal coated with your skin, and it can be deformed just along the curvature of your skin. And the actuator is using the similar platform we reported before, and can providing simple vibration force feedback. So the sensor, so you can see it's very sensitive, can distinguish different bending angles, and it's also very robust. Can working for like so 10,000 cycles, it's still working very good, and it can distinguish and working at a different frequency. So compared to the traditional human machine interface, only use our eyes. So the feedback is very important. Let me give you one example. So when you see something like a car is running very fast, it's rushing to you, and you try to do some action to avoid that. So however, so if somebody just punch your back and tell you just run away, you will go immediately. This is the difference between the reaction from the visual and the haptics. Okay, so then we integrate the haptic in the human machine interface, which can allow us to react very fast. And this reaction is directly send command to the robots. And you can see that the entire system is wireless, and all the devices just like this small. And you can control the robotic hand, this. So compared to the traditional, similar like axon skeleton controlled these human machine interface, our interface is very, very simple. And so you can even use this one to integrate with the robotic surgery robotics and to provide haptic feedbacks. Okay. So this is another application we mentioned. So for the COVID sample collection, so based on our interface, we know the current robots are using like a search system and using the manipulation joystick to control the swab and get some sample. Well, so this is quite rely on the expertise of the operator, so which may not save the energy resources significantly. So however, so if a person can use the VR glass to see the virtual thing, which is the really like a camera captured for the user, okay, or for the patient, and can control the like a sample collection, like this oral swab, I believe it can save a lot of time. So compared to the traditional COVID sample collection robots. So another thing we believe will be very useful is for the nursing robots. We know now it's a growing age in the whole world. So in next 10 or 20 years, we need a lot of robots or other technologies to help us to do the nursing. And here, so we show the possibility of our robotic VR system can control like a nursing robot and to do some simple like a nursing task and works, and which I believe is should be have a very great potential in this area. So overall, so all of these I mentioned is based on the haptic feedbacks. So we also read a very comprehensive review, so including all the different types of habitat feedback interfaces and according to different mechanisms and published in Materials Today Physics. And if you're interested in this area, so I think this is something that can save your time. So because we already summarized that. Well, so our next topic is the sensing area. So we know the human-machine interface, we mentioned the habitat, it's very important. So sensor, we also cannot overlook it, okay? So sensor, what I think is important is how about we use a self-powered sensor? So we develop some materials, so we call it the rubbery composites based on the PZT, piezoelectric nano composite, and the PNAS, and use the one-step screen printing method, can make a very large array. Well, such device is very sensitive and also shows a linear relationship with a different stress. So the advantage of such a system is you can use a very simple method to do one-step screen printing. and make a very high resolution array. It can even distinguish the like exact the curve, so the shape of your finger when you press it. So the resolution is very high, and the cost and the time, so it's very so different compared to the traditional ones. So based on such sensors, we can use the previous electrical circuits to control the robotic hand. You can see that. So it's very sensitive. Another thing I want to mention is this one is the voltage-based one. So self-powered, you don't need to use a voltage divider to collect the signal, directly give you the voltage signal. Very easy for the ADC to convert it to the digital signal. Okay, so another thing, so since we mentioned the self-power, another thing I'm always concerning, so several years ago, I was seeking the possibility to combine the self-powered technology, we know the triple electric nanogenerator, with the epidermal electronics. How can we make it very thin and self-powered? So we made some efforts. So the first work is we investigated, so the traditional like a flexible electronics, the design of the electrode, so influence on the performance of the TENG. So, and we make a different design with the different coverages, so the area. We find, so you can optimize the device with considerable stretchability. So at the meantime, the output performance is also very good. So which provides a possibility for self-powered sensing. And based on this work, so we further investigated the auto plan, so with a high stretchability. So we realized such we call the trampoline-based device. So make the device can be stretched not only in plan, but also auto plan, like shown here. And such device can provide even higher stretchability, up to 40%. And so which can be so integrated into array and like a skin electronics for mapping of these tactile information. Okay, and this is something I want to mention. So we made some efforts and do a lot of optimization of these functional materials. We finally make the TNG in a tattoo shape. This tattoo is just as thin as the toy tattoo you played when you are so in the childhood. So you can see, you can customize the shape and the pattern of the tattoo. And we make such tattoo in very thin format. It can generate very high power. At the meantime, the stretchability is very good. And we design the different shape according, I think so you can find one of your favorite. So based on your zigzag, right? So, and such a self-powered tattoo can also use as a sensor for human-machine interface to teleoperate a car. For the TNG, a lot of people claim it can be used for energy harvesting and powered electronics. So however, think about one scenario. If you want your device continuous powering, so I think TNG is some kind of difficult because it's the transit, right? So we want some continuous power like a battery. So here's another work and a series of work we want to mention to give the power solution in the human-machine interface. So we can use a SWITE to power the battery. We call the SWITE activated battery. So it's very simple, just to use a zinc-based battery or this magnesium-based battery. And we can use the flexible electronics technology, makes the device very stretchable and encapsulated with it. And so the device, after optimization with a different parameter, so the device can provide so like a 1 unit about 1 volt output. When you connect it in series or in parallel, you can either increase the voltage or the current. And so the first generation of the SWITE activated battery, so probably needs 0.5 mil per centimeter can make the devices working. You can see we use the artificial SWITE and also to whiten the device. When you whiten the device, and so you can see the change of the voltage. So first we use the ohm meter measure the voltage. So you can see Now the device is about like 1 volt, right? 0.9 volt. Another thing is so such a small sweat activated battery can activate it over 100 LED. Okay, so but I think this one's still too big. So but it can use in many areas. So such as we made a sweat sensors to use this one to power the sweat sensors for continuous monitoring these sweat. Such as the sodium, pH, and the glucose in the sweat. So I mean, so it's still too big. So we made some efforts on further shrinking the size and the thickness of the device. We make the device into a bandage lag, so which is for one-time use, and you can just mount it on the skin. And when you're sweating, so the bandage will provide you electricity to power the state-of-art sensors. So, and here you can see the differences between the previous first generation sweat sensor. And this is the bandage. You see, it can power the same amount LED with a greater brightness and in a shorter time. And such device can power such a small wearable sensor can monitor your activities and pulse rate and your blood oxygen level as well as the temperature, and in real time transmit to your cell phone via Bluetooth. So we can also embed it into some garments and also use another communication method called NFC, which is battery free. And of course, how to increase the sweat accumulation rate is another thing. We use the bio-inspired method, can connect with the microfluidic system to collect the sweat very fast. So here we use the lizard and the rice leaf, inspired microfluidic channel, and can collect the sweat. So you see, very fast than the previous one. And then, we for the first time realized the record high performance of the sweat activated battery with the power density over 100. And such device can also power a lot of wearable electronics continuous for a couple hours, no problem. Okay, and due to the time limitation, there are some other works I didn't mention, such as the bio-integrated electronics and some work, the materials and for the e-skins, and the sweat sensing I mentioned. So hopefully in the future we can have time to keep talking about these works. And as a summary, so we start from the materials and devices for the sensor and the actuators and the integrated electronics, to the system level devices. And in the future, we believe it can be applied in many areas and for some more important application. And at last, I would like to thank all my collaborators and the great support and from CityU. And also, I would like to thank my students and postdocs. Without them efforts, I don't think these works can come out. And at last, thank you very much. So I'm open for any questions.
Thank you, Dr. Yu. Thank you, Professor Yu, for your very interesting talk. And I was wondering if you can enlighten us on the major challenge for designing or developing these next generation actuators. I know you talk about the first generation and talk about the second generation with electro-tactile. So what is the major challenge and where are we heading down the road?
Okay, so I think the challenge is the challenge for me, I think it's quite a challenge to develop these skin integrated wearable format. Since the current Habitat technology, to be honest, I think it's very good, and you can have a lot of nice Habitats. However, it's very bulky. You can never use these, it's actively to seek some feedback. So you want some devices passively that mount on your body and provide the feedback as demand. So the challenge should be the mechanical mismatch between the current technology materials devices in these Habitat technologies and the soft time dynamic soft biotissues. That means our skin.